have done such a thing, but it's important. And Ziren is a MIPS-based zkVM. We started this project in 2023. 2023, and currently we already backed up some roll-up projects like the Go network. Okay. Why do we need to prove Geth? Okay. So to be honest, it's it's a very central topic in the GigaBase L1 ZK Day 2025 in Berlin. That's conference was led by Justin Drock. So first point is Ethereum is targeting scaling the gas limits to 1 gigagas, and so that means the gas limits still need to keep growing, but at that moment, I would say no executor really would like to replay all the transactions. So the answer is with the delayed execution and the zk proof. So that means the validators just verify the proof of the blocks of the transaction and without replay all the blocks. Okay. And another point is the zkEVM. zkEVM means the zk execution layer diversity. The execution layer. zkEVM diversity means the different EVM guest that's running as a guest program inside inside different zkVMs. Okay. So first look at this chart. We can see that guest actually is 41% of the total Ethereum nodes. But okay, most of the zkVMs can prove the Rust-based clients. So no one really have proven the Geth. So Geth actually is the dominant execution layer, but most of the EVM don't really do this. This is really, I think this is really a gap to the zkEVM diversity philosophy. So so here we've tried to fix the gap. The secret or the enabler is the MIPS. Okay, so actually Go compiler or have a very mature MIPS back end. If you want to compare a Go program to the MIPS, you just need to set up the Go arc to MIPS LE and then just run the Go build. And there's no fork from the toolchain compiler. Okay. The second point is MIPS actually is already better tested by the optimism fraud-proof VM. It's already the optimism have run the fraud-proof VM on MIPS in production for many years, and MIPS is very clear, well understood answers and have been used in production for 20 years. More than 20 years. I mean, for MIPS itself, it's had been a history of maybe 40 years. But for MIPS 32, we are using right now have been used for more than 20 years, stably. And Ziren is the MIPS is the first zkVM that implements the MIPS 32 ISO. And it's a general purpose zkVM for verifiable computing infrastructure for the unified settlements across the different blockchain ecosystems. And we have Ziren is very developer friendly. It's have a native support for the multiple high-level languages like Rust, Golang, C++. And we already have been audited by multiple teams regarding of the soundness, completeness of our sockets and emulator. So before we introduce how we prove the Geth, we have a framework about how to measure the performance. So yeah, it's we define a lot of us. I would think everybody every zkVM may have such a definition that's proving time equals to the instruction count divided by the proving speed. The IP means the instruction counters, instructions numbers from program P. That's compared to its ELF. And the proving speed means once we have the proving, have the ELF, then we run the we will run the emulator, we run the prover to prove all those ELF, all those MIPS, instruction sequence execution are correct. Okay. So for the PE, it usually means how many instructions the prover can procedure per second. And for the instruction count, we usually define, it's usually consists of 3 parts. The first part is the application logic. Like take the EVM, for example, it's included the EVM dispatcher, IRP encoding, decoding, and the roots, state roots computation. Yeah, and for the runtime, it's usually about the language itself. As we know, Golang have very, very complex runtime compared to the Rust, and it's also consists of like the stack, like the garbage connection, routing scheduler, yeah. And for the syscall, it's usually the the fat instructions that's used in your that's in your Geth program, like the cryptography operations, large number operations. Okay, so in this topic we focus on the instruction or emulator side. Okay, so actually it's very easy. Also, it's everybody can run it in your computer. Just clone your GoEthereum. Since we have some additional precompilers into the GoEthereum, so I forked it. Of course, we already have Kchak precompilers in the Ethereum master branch. Okay. So run those commands, and you can use the flag execute to just execute it. If you don't use this flag, it will prove it. But if you want to prove it, maybe you need a very powerful computer or server. Okay, so this is an example of that block, and with 407, it has 524 transactions. And what I want us to focus on is the syscall counts. You can take a look at the syscall counts. It consists of most of the top 3 will be about the signature verification, and the 4th one is the Kchak for the hash in the try DB state DB. Okay, so that's also the hard part we want to accelerate in the in this project. So before we really do, so first step is we want to decrease the count, the instruction count for the application logic for the runtime for the precompilers. So we need some principles. Like one we don't do is we don't change the Go compiler. So there's some type there. We don't change the Go compiler. We don't change the Go to a chain. But we need when we patch the Go the Go runtime syscall and the Go flags. Okay, So there are three layers here. The first point is when we, the first point is how we patch the Go runtime. When we load the ELF of the, at the loading time actually, not on the loading time, at the loading time actually we need to scan the ELF binary and find all the Linux API symbols, and then we need to implement all those, we need to make sure that all zkVM implement all those Linux API symbols. But of course, most of the Linux API, we just replace their implementation with immediate returns. So so like the file system operations, like the network operation system. And the second, and for the GC, we also disable with no opt-outs, the GC enable and reduct sweep credit functions. So that means we actually, the allocator in Golang runtime still works, but the memory will never be connected, but that's okay because after we finish the execution of the block of each block, the Go runtime will exit and the memory will recycled by the operating system. And we also disabled the scheduler. That means the Go routing in the Geth program will have no operating system to run against. Okay, so with this patch, it can reduce the lot of additional cycles. Yeah, the second one is the pre-compilers. Okay, replace the software cryptography primitives with zkVM syscalls. We just add an additional tags for the Geth, like go build Ziren. So that means we can use a same code base for both Ziren and the native execution. Okay, and this third one is also very subtle parts. That means we the MIPS zkVM is 32 machine, and for native execution it's run on the x86. So that means the layouts of the memory, the length of the words are quite different. So it's probably the hardest part of the engineering work when we do such a integration. Okay, this is this is all one I want to talk today. One sentence is we can control the overhead, the ratio of the Geth over the rest to 4x. That means the cycles produced by Geth is just 4 times that the rest produce. Okay, so this means it's really practical to realize the real-time proving in the future with Geth. Okay, actually we have run 10. We have run this benchmark on 10 consecutive blocks, and we have these charts from the 10 consecutive blocks within 81 overlap blocks. Okay, so the overall ratio is 4, but for some blocks that's without pairing is just about 7.8. Okay, so how do we actually patch the Ziren Geth? So here is all the patch status we have right now. We have the Keychack 256. It's the best. It's a baseline. It's already in the master branch of the Go Ethereum code. And another one is another biggest one is actually the zkEVM 256K1. It's from the EC recover. And yeah, we done it with some optimization with the Xiaomi tick. It can reduce the cycles with number like 56%. And we also have the pairing operations over the BN254. Yeah, it's already work, but I think it's still a bit slow right now. And for modex up to 256, yeah, it's already just takes seconds. Okay. So if and for the number that's for the operand that's larger than 256, it will fall back to the Golang. Okay, so for the KZG right now, it's the biggest gap right now because it's according to our experiments, it still takes a very long time to finish the execution. So actually, we need more optimizations over this point. And with the goal runtime, like with the goal runtime, I mean the timer, like the goal runtime time systems, like the war time, like usleep, we already patched it, so the Cisco actually be saved to 0 right now. Okay, so that's a path we achieve the 57% cycles reduction here. So the first point is we optimize the EC recover. Actually, it's also the summary from previous meeting with Phoenix. Yeah. Okay, so some other parts is also shaved a bit off of the cycles, and we still can that. The pairing is also takes 74% of all the cycles. So that's one we need to optimize in the next step. Okay, so back to proving. Okay, back to the proving time here. Actually, we already know the cycles, the instruction contents. We also have a number about the proving time. You can check out. Actually, everybody can check out the proving time from EaseProof, and there are more than 10 zkVM there, also included the Ziren. Okay, so it still takes about 8.9 minutes in average to prove a minute block. Yeah, it's too slow, but of course it's on single RTX 4019. We can scale it horizontally. And of course, get back to the 4x gap. I think we still need to look back to the IP here. I would say for the Geth, we already have patched the GC schedule. The go routing, and so for next step, I think the EVM optical dispatch IRP decode still have a lot of work to do because the REST have a lot of zk-friendly optimizations over there. For example, they use the sparse MPT, their Alloy IRP. It's very friendly to zk proving. So yeah, and for the next, for the completeness gap, we need to finish the proving of the BRS 12.381 modex that's operand larger than 256 bits. And for the performance side, we still have a lot of skills to go on, like FP6 and FP12 pre-compiles. Of course, with collaborating with Golang, Phoenix at EF, we aim to launch our one of 100 proving or EaseProof, and then the real-time proving next. So all the things are open sourced. If any one of you are interested in it, can clone it, run it locally. If you don't have enough GPU resources to finish the experiment, can contact me. I can provide you, our private proof network. Yeah, it's our Twitter, our Docs, our Medium. Yeah, thank you. That's it.
Thank you for our presentation. Maybe anyone have a question? No? Thank you.
Thank you.